Foundation Models for Embodied Decision-Making Agents, Part 21. Today I want to talk about world models. Do we need world models? What are they? And is this just semantic pedantry, or is there a fundamental difference between a robot that has a world model and a robot that doesn't? What does that actually mean? I'm going to put two papers in the show notes that discuss similarities between the subject. One is actually the paper is about predicting accurate scenes in a generative AI context. And the other paper, which is mentioned in the first paper, is about autonomous driving and having a world model. Now, the reason I'm mentioning those two papers is, first, I read those two papers, and the reading of the papers inspired this episode, and I think it's only right then to mention them. The point is the following, right? If you take the first paper, which is it's just saying, look, we want to be able to accurately generate scenes in a simulation, in a 3D simulation, right? That's a very, laudable endeavor, because if you can generate scenes in a accurate, realistic way, then you can have an agent potentially drive through that scene and learn how to drive. But the thing is, well, if you can already generate scenes in reality, does that mean you understand reality? And can you use that knowledge to potentially predict scenes? And now we're morphing into what's called a world model. Well, if we can predict the future from what we see today, then that's really what a world model is. And then the question is, well, fine. I mean, that sounds like something we could use, but what else is there? Like, how else is a robot supposed to drive? A robot is supposed to be able to predict the future in a context of, well, it obviously has to know what to do in every kind of situation. And whether that future is very long or not, and how much, and whether we have multi-token prediction or not, we discussed this recently. Those are almost technicalities. But in principle, I have to be able to predict the future. Otherwise, I can't move around. Take a human. Like, walking on the street right now as I'm speaking, there's people around me, there's cars around me. I'm predicting the future, obviously. I mean, I have to be able to have a sense that the car to my left is not driving towards me. It's parked, and it's certainly not going to drive because nobody's in there. And even if it drives, it's not going to hit me because the wheels are turning way away from me and stuff like that. So I can't predict the future. Now, if I can't, sometimes I can't. Cat jumps right in front of me and I step on its tail because I just didn't see it. I'm sorry. I mean, I just couldn't see it. I couldn't predict the future. I was wrong. My compute, it was intractable. This was an intractable situation, obviously. So the question, should we, and what is a world model? Like in the second paper where they talk about the world model, what they're saying is basically, well, look, how can we build a really accurate world model? And now let me say a few things about that. Having an accurate world model that is able to predict a scene in itself is not driving yet. I'm talking about self-driving now. We can, by the way, this is a tangent. All of this conversation can be used for let's say, humanoid robots, for any kind of moving object, right? We are just focusing now on self-driving. So let's stay with self-driving. But again, nothing wrong with extrapolating this into future scenarios where robots walk around in the kitchen or things like that, right? So back to the driving. So having, being at a crossing and predicting what's going to happen in the next 10 seconds, that doesn't necessarily constitute driving yet. It's a necessary but not sufficient condition, because obviously we also need to understand how to actually move our actuators. And in other words, predicting the future scenario of my environment and driving are not the same thing. A 15-year-old child can probably predict pretty well a scenario, mostly, but it, you know, he doesn't know how to drive, most likely. So he still has to learn how to drive. And that brings me to the crucial argument that we already made at CVPR 24. So this is a reiteration of that, which is, you know, having a world model or having understanding reality in a way that we can actually simulate it is a phenomenal step towards better self-driving. But it's certainly not enough, because we still need to learn how to drive, and we need a reward function for that. And the reward function is potentially implicitly learnable with the world model. And this is kind of where I want to go with this episode, because what this paper inspired me to read, what they inspired me while reading, is probably an understanding of what Tesla is doing. And I apologize for listeners that I'm trying to always circle around what Tesla's doing without really knowing what they're doing, and that's because they're not talking about it. And as an investor in Tesla, I wish I knew, but I just don't. But I could probably gather from most of what's being published that they're somewhere in that realm of what's being published. And these two papers, in my opinion, are very interesting, and I'd be very surprised if Tesla is not leaning heavily towards some of these concepts. So one is the realistic 3D generation of future scenarios, and including semantics. This is a new thing. This is something we've been talking about for a while already. The power of large language models, video language models, and the combination of being able to learn all these things implicitly should enable a more semantically oriented vision stack. In other words, I can see children on the road, and I can infer from children on the road. I can predict that there's a pretty high likelihood that they might actually jump on the road, so I might want to slow down. So that's something that we don't see right now in FSD12. And the other big insight from CVPR 24, of course, was the actual reward function. What does it mean to drive well? That's not so clear. And Tesla has it because of all the driving. Now, you know, the imitation learning, and we've spoken about this. But what I want to say here now is that there's a potential to actually have a world model that does both. Because predicting the future, in principle, really means also understanding what I'm going to do next. And even going down to the low-level technicalities of how to actually execute it. In other words, what is the actual gas pedal push that I need to exercise, and how much, you know, brake do I need, and all of that stuff. So there's a potential that you can have a world model. It's just a different nomenclature. That, you know, the FSD is just called the world model. That's it. And I'm going to drive according to that world model. Now, there's another potential implication, which is to separate those two things. So to have a world model which predicts the future, including what the model thinks you should be doing, and then there's a separate network which is trained on and executes low-level actuators. And whenever these things don't match, you have some sort of maybe Byzantine general type solution where you converge towards, again, what maybe a network, a third network which optimizes if they don't match. This is me conjecturing. What I'm saying is, like, you don't necessarily have to have one model. You could have two or even three models. You can have, like almost like a GAN type model where you have a discriminator, where you know, a third model that discriminates between the actuator low-level stuff and the high-level world model stuff. How the actual implementation of engineering is done, that's very interesting. But in this episode, I think I want to just focus on the big picture question again. Do we need a world model? And what does it mean to know how to drive? Are these things the same thing? And the answer is not necessarily. We could have a world model which is very good at predicting future events, including the agent's behavior. We could have a separate model which is trained to drive and has low-level actuator implementation, and then we could have a match of those two, and whenever they mismatch, that's when we have a discriminator which decides which one to use, and let's say the world model being the ground truth. This brings me to the question of ground truth, which is another, in my opinion, very fundamental question. Ground truth is something that is being thrown around in AI all the time, and in many cases it's almost straightforward, right? If I want to classify cat videos, well, the ground truth are just all the videos that I'm learning from. If I want to classify, what is a good Shakespeare poem, and let's say train GPT to give me a good summary, or actually to even give me a poem of Shakespeare. Ground truth becomes a little bit more hairy, but let's say we have reinforcement of human feedback, so we have people actually telling, experts telling the model what is good, what is bad. If we have coding, what is good code, what is bad code, you can see where I'm going here. And now, which means it becomes a little bit more difficult to decide what is actually good coding. And in particular, when we have sparse rewards, let's say in the case of coding, I want to write an app that, I don't know, schedules robo-taxis. Well, what is a good app? What is good code? How do I even define that? And of course you could say, well, good code is just the app that does the job. Yeah, first, that's very sparse reward, but more importantly also, well, what does the job then actually mean? So you see where we're going here. And with driving, this is even more extreme, because good driving means a lot of things to a lot of people. And at CVPR 24, there was this the Waymo person, forgot his name, Russian name, the person that runs AI at Waymo, or he's the CTO of Waymo, something like that. He mentioned that the world model, the reward model is not really known yet. So even if we have a very good representation of the world, a semantically embedded, intelligent representation of the world, even then, even in that scenario, it's not a foregone conclusion that we can just learn how to drive, whether it's in sim or in real, because we don't quite know what driving means. And a lot of it is sort of trolley problem related issues. And when I say trolley problem, I don't necessarily just mean the life and death type stuff that Philippa Foot was talking about in her seminal paper. It could be just simple stuff, right? If I turn right now, I'm gonna endanger somebody else, and in principle make myself safer, but that somebody else could get hurt, and maybe that's not such good driving. Maybe I should be more cautious. So we have a lot of edge cases here. Good driving is not a solved problem. And I think that's where the Tesla advantage comes in, because Tesla has a data set that actually constitutes good driving. And we could argue that that should be something that maybe should be public at this point, but that's a different conversation. So to summarize, I think what these papers mainly give us is an inspiration to think about what is a world model, what does it mean to understand the world, and in the context of driving, does it imply that you also know how to drive? And the answer is yes and no. You could have an implicitly trained model that encompasses the world as it is, so predicts the future, including the own agent's actions, and then have basically that model also drive. That would also require the model to have the low-level actuator type information and weights, which is of course possible. Or we could separate these two. And I don't know where, let's say, companies like Tesla live right now, but separate means you have this world model. Think of it like a frontal cortex. Like you're thinking, okay, where should I go? What's going to happen? And then you have sort of the low-level actuator type information where you actually execute, gas pedal, brakes, things like that. And then you have a discriminator that if those things don't match, so if you're low-level actuator type, weights lead you towards a scenario in the next, let's say, 2 milliseconds or 2 seconds, I don't know, something like that, where you're going to deviate from the world model, then there's going to be a discrepancy, and that needs to be taken care of. And I think further thought about this is required. We're definitely going to keep working on this because this is really fundamental. This is fundamental for self-driving as much as it is for the rest of robotics. What does good behavior mean? And what is an ideal environment and an ideal trajectory of the environment? And how does good behavior and an ideal trajectory of the environment match together? And how can this be all incorporated in one model? Those are very interesting questions. Thank you.